Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, good morning everybody. Thanks for coming. Today's speaker is Bruno Oliveira, who's did his PhD at Oxford on generic programming, so it's an advanced form of Haskell, for those of you who don't know, and he's worked on a broad range of other programming paradigms, so object-oriented, aspect-oriented programming, monads, clock, lots of good stuff. But today he's going to tell us about algebra-oriented programming.
Okay, thank you very much. It's a pleasure to be here and have the opportunity to present my research. And what this talk is about better programming abstractions for dealing with cross-cutting concerns. And so you might want to ask, why do we want this in the first place? And the reason why we want this is because there's a real need for it. In industry and in software engineering, people these days are trying to build really modular pieces of software. And in order to build these pieces of software, they really need to have a good handle on cross-cutting concerns. There are some solutions out there that already help you with this. But these solutions, okay. Can we wait for slide 2? Okay. But these solutions are typically based on code generation and code manipulation, and they tend to be quite brittle. So what I'm going to suggest here today is that instead we should try to look at this problem at a more fundamental level and try to come up with programming language abstractions that help us to design software that deal with these cross-cutting concerns. And I'm going to make a concrete proposal for this, which is to use algebras, which I'll explain later in the talk. So what's a cross-cutting concern? Basically, a cross-cutting concern is some code that is logically representing a feature in a program, but it turns out that the implementation of this feature is all spread out across the code of your program. So, for example, if you have heard of aspect-oriented programming, you probably know that aspect-oriented programming helps you dealing with one type of cross-cutting concerns. And these cross-cutting concerns is what I call homogeneous cross-cutting concerns. So what happens in homogeneous cross-cutting concerns is that typically you have kind of the same code appearing in multiple locations of the program. And so what aspect-oriented programming allows you to do is to modularize this code in a single location and then simply instrument the program at the right places. So it allows you to modularize this kind of code. There are other types of cross-cutting concerns. And the type that I'm going to be mostly interested on today is what I call an heterogeneous cross-cutting concern. So an heterogeneous cross-cutting concern is code that belongs to a feature, but instead of being the same code in multiple locations, is just different code in multiple locations, even though it logically belongs together. So let's look at this example to explain these heterogeneous concerns in more detail. So suppose you're trying to build an interpreter. So if you're building an interpreter, and if you decide to do it in an object-oriented way, one thing that you might do is start by having an interface, let's say an interface for the expressions that you have in your interpreter. And in this interface, you place some of the operations that you want. Let's say that you start by implementing the pretty printer of the interpreter. So that's the simplest thing to implement. So you go on and design an interface with a single method. That's this printing method. And now you implement a number of classes, one class per each type of expressions that you have. And for each of these classes, you go on and implement the printing method. So now, suppose that you decide to implement the evaluation function for this interpreter. What do you need to do? Well, essentially, what you need to do in an object-oriented language is that you essentially need to go and edit the code everywhere. And you need to do this because you need to now add a new method to the original interface, the evaluation method. And for each of the classes that you implement, you need to go and implement the evaluation method. So you need to define the evaluation method for each of the constructs in your language. Evaluation, in this case, is a cross-cutting concern because it requires code that is spread out across several locations in the program.
True whenever you add a method to an object, to an interface. Mm-hmm. Is that not true whenever you add a method to an interface?
Yes. It's essentially, it's exactly that problem. Yeah. Okay. So adding a method to an interface generally creates a cross-cutting concern. Okay. So why do we want to modularize cross-cutting concerns in the first place? Well, the software engineering answer for this question is because essentially what you will want to get is to get large-scale reuse. And this is actually a diagram that I borrowed from Linda Northrop. She works in the CMU Software Engineering Institute. And it's a nice diagram that kind of describes the evolution of reuse during times. And so if you go back to the 60s, so in the 60s we created subroutines. And what subroutines do is that they allow you to capture small portions of code, put them together in a nice abstraction, and then you can just go and reuse this portion of code by instantiating it multiple times. In the 70s and the 80s, we came up with modules and objects, and then this allowed us to modularize larger portions of code. So we increased the reuse. Then Linda argues that in the 90s and the 2000s we had components and services, but eventually she ends up with today. And what she argues that we have today, which is the ultimate form of abstraction, is what she calls software product lines. And software product lines are this ultimate kind of abstraction that allow you large-scale reuse. So what's a software product line? Basically, the software product line is this idea of having a set of highly reusable components where each component represents a feature in the programs that you want to develop. And the idea is that you can, if you want to design a new program, what you need to do is grab some of these components, you put them together, and you compose them nicely. Maybe you tweak them a little bit for the particular application that you have in mind, and then you get one program. If you want to develop a similar program, but not exactly the same, you go and do the same thing. You take some of these components, you compose them together, you tweak them a little bit to fit the particular application, and then you get another product.
So can you give an example of a software product line?
Next slide.
Okay. I'm not sure what it is yet.
Okay, but anyway, the idea is that you have a family of products. All of them are very similar, but they all have a small portion of variability. But essentially, if you want to implement these software product lines, what you need is a good way to deal with cross-cutting concerns. So what's a concrete example? So Nokia, for example, uses software product lines to develop their software for phones. And the reason Nokia needs this is because they have hundreds of models of phones. And each phone has a different number of keys, different display sizes. You have to deploy these phones in different countries with different languages. So for Nokia, the key question is how can you develop the software for all of these phones in a cost-effective way? Of course, one way in which Nokia could approach this problem would be that they would take the first phone that comes, buy the first model, they develop the software from scratch for that model, and then they take the next phone that comes along, and what they do is they simply copy the software from the first to the second, they patch it a little bit, and they get the software for the second phone, and they keep doing this. But what's the problem of doing this? The problem is that if now you have a bug, for example, now you essentially have to go and fix the code for every copy that you have done for the system. And this code is modified, so it's not an easy task. So it's really a maintenance nightmare. So instead of doing this, what they do is that they use the software product line technology to have this set of highly reusable components that they can just use in all of their phones. So that if you have a bug, you fix it in a single location, and the bug gets fixed for all of the phones, essentially. So that's the idea. So there are many other examples in industry. Actually, there's in the software engineering community, there's a community that deals with these software product lines, and they have a Hall of Fame. So if you are interested in seeing some other applications of software product lines, you can go to their webpage and check some of other case studies. But okay, so how are these companies developing software product lines? So what tools do they use? There are tools out there. So two popular ones are Head and Feature House. And what these tools do for you, or the way these tools work, is that they use what is called superimposition. And superimposition is basically a syntactic way to compose code. So suppose that you want to develop a software product line for Java programs. So the idea is that you would go and use one of these tools. And what these tools provide you is a superset of Java. And what this superset of Java gives you is some language constructs that essentially allow you to say things like, if you compose this module with another module, then just fetch some methods from the other module and copy them into these classes. So it's essentially a very syntactic way to compose code. You're just composing the text of your code rather than composing the binaries or something. So, so what's the problem with this solution? Even though it's very powerful and people have developed large software product lines with it, it's very brittle. And it's very brittle because it essentially becomes very difficult to have any form of modular type checking or separate compilation, or more generally, any form of modular reasoning. So, for example, if you want to type check the software product line, what happens is that you take these modules that are written in this superset of Java, you compose them, and then the tool generates some Java code, and only after getting this generated Java code, you can now run the Java compiler and get some typing errors. So if you get some typing errors, essentially you get them from the generated code instead of the code that you have originally written. So something analogous to this is C++ templates. So if you're familiar with C++ templates, C++ templates are pretty much using a very similar idea to tools like a Head and Feature House. So what happens in C++ templates is that you have a template language that you write on top of C++, and what this template language allows you to do is that whenever you instantiate the templates, you get some generated C++ code. But the problems are very much the same as with these software product line tools. So basically, it becomes very hard to get modular type checking, becomes hard to do separate compilation, and you typically have these nightmare error messages because the error messages are in terms of the generated C++ code instead of the modules that you have written in the first place. So what's the solution for this, or what's a better way to do something like templates? Well, people in this room, some of the people here, have actually worked on doing something better than templates. They have developed generics for .NET languages. And what generics give you is that they are semantically integrated in the language. So they are not something outside of the language. They are just part of the language. So they are perhaps not as powerful as C++ templates, but they are powerful enough. But they are much more robust. And they are much more robust because now you get properties like having modular type checking, you have separate compilation. So if you have some type errors, these type errors are really in terms of the code you have written in the first place and not in terms of the generated code.
So by generic set, you just mean parametric polymorphism in the style of ML, do you?
Yes.
Okay.
Yes. Well, in the case of object-oriented languages...
Very much less powerful than templates, I mean, isn't it?
Yeah, sorry?
It's very, very much less powerful than
Templates are kind of a Turing-complete language, so you can actually do... But I guess in Haskell you also have a Turing-complete...
Parametric polymorphism doesn't really address the challenges you were outlining earlier, does it?
No. I'm just giving an analogy here. Just saying that the problem that I'm facing now is that we, at the moment, what we have is this. Okay. And, well, basically what I'm going to suggest is that we should have... now, instead of using code generation, why don't we do something like we did with generics? And instead we create some programming language abstractions that deal with this problem in the first place. So that's my suggestion. But anyway, so before I discuss my solution, I just want to make it clear why aren't existing programming language abstractions enough to deal with cross-cutting concerns. So the basic problem is that existing programming language abstractions, say object-oriented interfaces or algebraic data types in Haskell, they are typically very good at modularizing your code in a certain way. But they are not so good at modularizing your code in some other dimensions. And this is what creates cross-cutting concerns. And many people have already made this argument before. So, for example, aspect-oriented programming arose from this issue, but perhaps the work that summarizes the issue more clearly is Philip Wadler's expression problem. So, in the expression problem, in terms of this cross-cutting concern perspective, is essentially telling us that no matter which paradigm you choose, object-oriented programming or functional programming, you will always have to face a choice in terms of these cross-cutting concerns. If you take object-oriented programming as a starting point, then adding new variants, which corresponds to add a new class, is easy. So in the context of our interpreter, if we wanted to add a new type of expressions, then this is easy because you can simply add a new class, and this is very modular. You don't have to touch any code. But if you want to add operations in all languages, then this is hard because now you have to go and change all the codes that you had before. If you switch to functional programming, you have the dual problem. So if you develop your code with algebraic data types, then adding operations becomes easy, but adding new types of expressions becomes hard or cross-cutting because now you have to go and change or edit the old code. So actually the expression problem is a challenge, poses a challenge to us, which is basically how can you modularize your code in a way that you can have modular variants, modular operations with full modular type checking. So that's the expression problem from this cross-cutting perspective. So what I'm going to propose is that instead of using object-oriented interfaces or algebraic data types, we could be using algebras as a programming abstraction. And what I mean by algebras in this talk is essentially a form of algebraic signatures. And algebraic signatures were very popular in the 70s, and they are closely related to abstract data types and also closely related to ML modules. But essentially what they are is that they are a kind of form of interface like this, where you have an abstract type E, and you have a set of operations defined on this abstract type. So for example, if you wanted to model some simple form of expressions just with literals and addition, you could have two methods like this, which are basically have the signatures of the constructors of those expressions. So why are algebras better or helpful or more helpful than other programming language abstractions in terms of cross-cutting concerns? Well, essentially because they support multi-dimensional modularity. So they are not modular in just a single dimension. They are modular in many dimensions at the same time. So they support composition operators for each of the dimensions of the expression problem, for example. So for example, you have this combine operator here. And this combine operator is what allows you to compose in a modular way several operations. The idea is that you have an algebra, F, and you can understand this type A as being the operations in your system. So you have two operations, A and B. And this combine operator allows you to create a new algebra that contains the composition of the two operations.
We had X bulge of E. So in this slide, is the X bulge part the F part and the E part?
Okay. So this corresponds to the F, X algebra, and this corresponds to the A.
Okay, so the A part is the type over which you're going to operate. Right. It's not the operations.
It's the type. You can view it as the interface of the operations that you are going to operate. It will become clearer in a minute. So, okay. So this combinator essentially allows you to deal with modular operations. If you want to deal with modular variants, you need another combinator, which is what I'm going to call the union. And this takes two different algebras, F and G, operating on the same type, A, and it composes the operations of the two algebras into something that operates also in this type A. So basically, this is what allows you to have the two forms of modularity. But you can also have other combinators, like, for example, things that decorate the algebras with cross-orthogonal concerns like logging and tracing or security. And furthermore, the other nice thing about algebras is that there's a lot of theory behind algebraic signatures already, and algebra of programming and all that. And there's already some support for proving. So you can actually support not only modular definitions, but also modular proving about these algebras. And the other thing is that you can represent these algebras concretely in different languages using different representations. So if you're a functional programmer, you might have heard of F-algebras, and F-algebras work very well in functional programming. If you're an object-oriented programming, you can use another representation, which is object algebras. But there are many different representations that you can use. OK, let's look at some code. OK, let's go back to this interpreter example. And now let's try to see how we can develop this interpreter example in a more modular way. So this code is written in Scala. And if you're using an object-oriented language, you can model these algebras very directly, or these algebra interfaces, by just using a generic interface. So this keyword here, trait, you can read it as interface in Java or C#. It's more or less corresponding to an interface in Java or C#. And then this is essentially an interface which is called X algebra and has a generic type E. And this generic type represents the abstract type. And what you have is you have two methods which represent the constructors that you have in your small algebra of expressions. So when you look at this, this is actually very similar to an algebraic data type, say in a functional language like Haskell or ML. So if you would be using Haskell or ML, you would create an algebraic data type with two constructors, lit and add. And algebras or algebra interfaces make you think about your programs in a very similar way. So you think of your programs as kind of grammars for the grammars of your constructors, of what you can construct. But then the idea is that if you now want to create a new feature, you create a feature interface, and that's the interface of your operations. So if you want to implement pretty printing, for example, you can create an interface iPrint with a printing method. And now to implement this feature,
I thought that was going to be iPrint of E with type E to string.
No, because this iPrint is going to be replaced by this E here. So you're essentially, when you implement an algebra here, okay, this is an actual implementation. So you instantiate the algebra with this interface here. And the idea is that the printing method, so the reason why you don't have E here is because you, in object-oriented programming, you have the self, right? So the E is the self. So you're thinking of the self argument. So that's the argument that is missing here. So and for example, how you go and implement the lit case, the literal case, is like this. So you just go, you want to implement the literal case with this method. So you define the printing method, and the constructor already gives you the argument, x, and all you have to do is call x.toString. Okay? So this is very similar. So there's a little bit of verbosity here just because it's object-oriented programming and Scala, but is very similar to defining a function by pattern matching in Haskell. So if you would define the code for this in Haskell with an algebraic data type, you would end up writing something very similar to this. Case lit x equals to show x, basically. So that's what you do. And it also works, of course, with recursive constructors. So you, what you get is objects that have the printing method, and you can call the printing methods like this. So print the first argument, put the plus in the middle, and then print the second argument. Okay. So how about adding evaluation? Okay, if you want to add evaluation, then now just create a new feature interface. So you can create a new interface for evaluation, and so that has the eval method. And now if you want to implement evaluation, you simply instantiate the algebra interface with this feature interface, and now you go and implement the evaluation methods again, in a very similar way to what you would do in Haskell. So, for example, in the addition case, you have an object E1 which has the eval method, so you can call eval, and then you add that to the result of evaluating E2. And the point here is that adding this operation is done in a modular way. So I didn't have to go and edit existing code. Sorry.
Simple question. So you're using Scala. Is there a reason why you couldn't do this in C# or Java?
You can do this in C# or Java. Yeah. Okay, but the point here is that this code is modular. So now, unlike the code I've shown before, I didn't have to go and touch existing code. So how do you do variants? So for example, how do you add a new case now to your expressions? Okay, if you want to add a new case, okay.
So are you going to show how you have something that can both be printed and evaluated?
Yes.
Okay.
Okay. So if you want to add a new variant, now what you do is that you create another algebra, which could either be an extension or could be an independent algebra. But let's say you create this algebra for subtractions, minus. And now what you need to do is go and extend the existing algebras with this case. And essentially, again, this is modular. All you are using is subclassing. So again, adding a new variant doesn't involve cross-cutting concerns. So you don't have to go and edit existing code. It can all be done in a modular way. So how do you compose these codes and assemble different products? Well, the first thing is that you need a way to create data, right? So you want to create data. How do you create this data? The idea is essentially that you have some builder methods, like exp here. And what these builder methods do is that they take an algebra as an argument, and then using the methods of this algebra, you can create different values for your data. In this case, you have 3 plus 4 here. So just by invoking the methods of the algebra. But the key point is that you always, when you create this data, you always create it in a polymorphic way. So this E here is not instantiated to a particular type, it's parametric on this type. So this is an abstract type. So it's creating data of some abstract type. One interesting thing about this code is that you can create data from different types of expressions. So for example, you might have a type that supports only literals and addition, and you might have another type that supports literals and addition and subtractions. And these types are compatible with each other in certain ways. So for example, you can use this builder method here to construct data of this larger type. Okay, so how do you now go and create some objects that actually use all this infrastructure? So the idea is that if you want to create objects, what you need to do, so these objects are the particular programs or the particular types that you want to use. So if you want to have an evaluator that has both the method eval and the method print, what you need to do is to use a combinator, this combine that I told you about in the previous slides. And this combine takes the two algebras, puts them together, and creates a new algebra whose type is actually the intersection of these two types here. So actually, I should mention here at this point that, so this is actually something you only get in Scala. So you don't get this in Java or C#. You can also work in Java or C#, but where you would replace this width, this intersection type by pairs, but it's not as convenient. But you could model this with pairs as well. But okay, then one nice thing about Scala is that you have these intersection types, and these intersection types capture this, allow you to write this combinator that composes the interfaces of the objects. And what you get here is an object that contains the two methods here. So you can actually call the evaluation method, and you can call the printing method. But you can have other variations. This is the point of programming in this style, is that you can have multiple variations. You can have objects just with the eval. You can have objects just with the printing method. You can have objects that, for example, create an evaluation method that is decorated with logging information. And all of this is done in a modular way. So you don't have to go and edit the previous code. So all you use is combinators that basically introduce either new behavior or compose the existing behavior together. Okay. So just to give you a history of how did I came to this. So I did my PhD in Oxford, and in Oxford there's this very mathematical tradition on functional programming, and in particular they have this what is called the algebra of programming. And one of the key ideas of the algebra of programming is that you use faults. You use faults to write programs. You use faults to reason about your programs. And actually, the algebras that you have seen before, what they are effectively is that they are these fold algebras. So when you write an algebraic data type like the data type for expressions, you would write something like this. You would write, well, I have a data type for expressions, and this has two constructors, lit and add, and the lit constructor takes an integer and returns an expression. The add constructor takes two expressions and returns a new expression. So what this algebra does for you is that allows you to essentially replace each of these constructors by the function, by these two functions. Those are the functions in the algebra. to get some new type E as a result. And my inspiration and how I started working in this line of work was that I read a paper by Rolf Inze, and Rolf Inze had this nice representation of fold algebras as type classes in Haskell. And there, what he was trying to do, he was trying to provide a generic programming library without using some sophisticated language features. But there was an important limitation of his library. Basically, the library had limited use because it didn't allow one form of extensibility. Essentially, the problem that Ralph was facing was the expression problem. And this is how I got interested in this line of work. And kind of my first work, my first research work was exactly on how to try to get rid of this limitation that Rolf had. And what I did was, still in Haskell, I used type classes and the subclassing, type class subclassing mechanism to basically modularize these algebras and compose the algebra signatures. And with this design, I was able to overcome the limitation that Ralph had and essentially provide a solution to the expression problem. Okay, after I'd done this initial work, some other researchers came along and they decided to employ very similar designs to modularize DSLs. And this is perhaps the main success story that I have to tell you about these techniques. So early on, still in Haskell, some people have shown how you can use these representations to modularize domain-specific languages, or embedded domain-specific languages. And then this technique was ported to Scala, actually. And in Scala, this line really picked up. And these days, there's a large infrastructure for modular DSLs in Scala, and the idea is, again, is this idea of a software product line. So you have this set of components of DSLs, and basically these components represent different constructs that you might have in a domain-specific language. You might have a small language for arithmetic expressions, you might have a small language for booleans, you might have, I don't know, statements. And the idea is that you can just go grab the features that you want to have in your domain-specific language, then perhaps have the domain-specific constructs that you need for your language, and then you're done. The advantage, of course, is that if you want to have an optimizing compiler for your domain-specific language, you don't have to write it from scratch. What you do is you just reuse these components, and what you need to write is only the code for the new constructs of your domain-specific language. And this is now a very popular approach in the Scala community. Anyway, I've continued my research in this line of work, and what I did after working in Haskell was that I was very curious to see what these techniques represent in object-oriented programming. And what I found out is that they are closely related to the visitor pattern. And so one of the first things that I did was show how can we improve the visitor pattern to make it more modular. So again, the visitor pattern, what it allows you to do in object-oriented programming is that it switches the advantages in terms of cross-cutting concerns. So you can make an object-oriented language become more functional in the sense that now you start modularizing operations instead of modularizing the variants. And what I've shown is that you can have, what you can now have is that you can do modular visitors. Again, you don't have to make this choice as you do between functional programming and object-oriented programming. You can design visitors in a modular way. But what I've done more recently is simplifying all of these techniques. And this simplification is essentially the code I've shown you previously. And I call this simplification object algebras. And this was essentially the code that you have seen before. And the nice thing about these object algebras is that they provide you a nice technique that you can use in mainstream languages, including Java and C#. And you don't really need advanced features. All you need is essentially a standard object-oriented language with generics in it. If you have that, you can program in the style that I've shown you before. That's all you need. And this was the first solution that was kind of worked in such a simple way in a mainstream language. I've shown a few more things. So I've shown that this actually scales to more complicated cases. For example, you might have, in the general case, you might have several mutually recursive types that need to be extended. And actually, these techniques also scale to that case. And more recently, what I've been working on is dealing with feature interaction. What is this feature interaction problem? So basically, feature interaction is this idea that sometimes features are not nicely orthogonal, like printing and evaluation. Sometimes when you compose features, they need to interact in some ways. And how do you specify the interaction? That's the question. And again, what you can do is you can have a generalized combinator or composition operator that allows you to specify how these interactions happen. And what this combinator looks like is essentially it looks like a zip width in functional programming. So it's very similar to the type of a zip width. Okay, so for the last part of my talk, just want to tell you that you can also do modular reasoning. So it's not only the case that you can develop the software modularly, you can also prove things about this software. So one of my most recent works is this Meta-Theory a la carte, which was presented in Popple this year. And the idea there is that, well, programming language people are interested in formalizing meta-theory of programming languages. But in order to formalize, this formalization process tends to be quite monolithic in the sense that you go and formalize meta-theory for one language, and then you have a small variation of this language. And what you need to do is just copy the code and modify it in a number of places, and then you get a new development. But if now you need to change something, then again you have this nightmare problem because now you have to change all the copies. So what we've provided is this framework where you can actually have these modular definitions and proofs as well. So you can actually modularize the definitions, you modularize the theorems, and you modularize the proofs. And the key challenge that we have solved is how do you come up with the proof methods to make these partial proofs, because you cannot just use standard induction because that's a closed principle. So you need to have some form of modular induction. And actually, again, if we go back to this algebra of programming and we look at universal properties of folds, we can, from there, derive modular induction principles. And that was kind of the main result of our Popple paper. And just to quickly tell you what we are now working on is how you can also deal with components with side effects, because side effects also they cause trouble, and you have to model these effects. So our framework, our initial framework could only deal with pure languages, but what we are using now, and this is a paper that we have just submitted, is that we use monads and algebraic laws about effects to also now have meta-theory for languages with effects. So we can deal with languages like this, for example. So this is kind of the languages that our framework can deal with. So we have components. We have 5 sets of components for arithmetic, Boolean expressions, lambdas, references, and errors. And these two use effects. So you actually have to to have a way to do proofs about exceptions and state. But the point is that we have components that are fully modular for these 5 language features. And with them, we were able to recover 23 language variants. But these 23 language variants use a single code base. So you're not copying the developments. So you're just reusing the same formalization for every one of these 23 language variants. So what we have essentially is something that looks like this. We have a set of components. We can have features for arithmetic, we have the functions for arithmetic, we have the theorems, we have the proofs, and we can just pick some of these, put them together, and then maybe if we need to prove meta-theory for some language that uses our own extension, we can just add our own extension, and this is how you would go and prove the meta-theory for your new language. So you can just reuse the existing development rather than copying or pasting it.
Just explain something about feature interaction here. Because something like, I don't know, the order of evaluation of expression affects the way exceptions propagate, or effects certainly. I mean, that's side effects. So they're not. You can't just snap them together and expect everything to just work.
That's true.
You must be hiding something here.
Yes, I didn't mention feature interaction, but you're right. So, for example, there's an interaction between state and exceptions, and so what we do is that whenever you compose 2 features that use different sets of effects, you also have to specify some laws about this interaction. So for example, with state and exceptions, there are actually 2 reasonable semantics, which is you can either propagate the state or not. So, and each of these 2 semantics kind of gives rise to a law that specifies how the interaction between state and exceptions should work. That's essentially how you do the interactions.
In that particular case, there are lots of papers about that, so you knew exactly what to do. If you just took 2 random things and you threw them together, you have a systematic way to discover exactly what the interactions are.
No, you have to study. You have to study the interaction. You have to go look at it and figure out essentially how the interaction between the 2 types of effects should occur. So of course, what we have done here is that we have modularized things that we already knew, the semantics. What we haven't done yet is to investigate, like how now I compose this with something new that hasn't been studied before. But the idea should be that you need to figure out essentially how the operations with effects interact with each other. So in the case of state and exceptions, you want to figure out how catch and put work together, for example. And if you add a new type of effects, you need to figure out this. Okay. Anyway, just to summarize kind of the contributions that I've done in this area. Well, first of all, I think the main point that I want to tell you today is that algebras are really a promising abstraction for cross-cutting concerns. I think this is the key point. But so one nice thing about algebras is that they have solid theory behind them. So this is not like, for example, aspect-oriented programming or these tools for dealing with software product lines where people are just figuring out ways to syntactically compose the code. In here, there's an actual mathematics that you can use to reason about these algebras. But okay, so the first thing that I've done was really to show how, give nice interpretations of these algebras and show how they are helpful in terms of modularity in both functional programming and object-oriented programming. So that was my early work. And then more recently, I've shown that if you want to model algebras, you don't really need sophisticated features. Actually, most languages that we have out there already have the basic support that you need to program with these algebras. So in object-oriented languages, as long as you have a standard object-oriented language with generics, you can probably get most out of these algebras already. And I've shown that you can actually extend these techniques to more realistic cases, like the cases where you have several mutually recursive data types evolving at the same time. I've also looked at how to support modular proofs, and modular proofs which allow you to do modular proofs by induction and also modular proofs with effects. And then I've shown that this is highly compositional. So the object algebras really allow a very compositional way to develop your software. And I have some case studies and perhaps a success story. But okay, in terms of future work, what I really want to do is to work more on programming language design. Even though we can now model program with algebras in existing languages, it would be better if we had a programming language design that supported algebras from scratch and supported all these composition operators as a language construct instead of encodings. I think this would lead to a more natural way to program with algebras. And I also think that we need to, another thing I need to do is to try these techniques on larger software product lines. So I've tried some medium-sized software product lines, but not something that is really, really big. So I think this would be something that I would like to do. Okay, to conclude.
When you presented the Scala code or the C++, C# code, it kind of looked fairly direct. Is it an encoding or does it get clumsy? Is there a big win to be had here?
Well, there's still... what you would gain would be, for example, in terms of the composition operators. So, you have a kind of hierarchy problem in Scala. So you need composition operators for different arities of your type arguments. So, for example, you have, if we're talking about Haskell, you have types in kind star, and then you have types in kind star to star. And again, you need, if you want to have algebras that operate in all these kinds, you would need to repeat the infrastructure for each of these kinds. So if you have a proper language design that supported these composition operators, then this would be something that the language itself would deal with, rather than you having to repeat code. So it's a typical problem in generic programming libraries. Yeah. So, and the other thing is, of course, that I would still prefer the Haskell version of that code. In Haskell, so if I wanted to write the evaluation function, it would take me 2 or 3 lines. In that Scala code, I still have to some verbosity, and that takes like 7 or 8 lines. So, I mean, there's some verbosity just because of the syntax. Okay, but anyway, I think I said the main points. So I think cross-cutting concerns can be solved at the programming language level. So that's the key point. No need for ad hoc extensions. And there's still lots of work to be done. I guess I should stop here.
Okay, thanks very much. So we had quite a few questions, but we've probably got time for one, maybe one more.
Sure.
Right at the back.
And maybe this is an example of a feature interaction you were talking about before, but what happens when you can't get this nice separation? For example, you even actually had an example between a val and print, where for certain forms of expression they were 2 totally separate things, but for printing the addition, that didn't make sense unless you had the ability to do an evaluation too, because your print wanted to have that as part of it. So do you lose all of your modularity as soon as sort of even one version of it links them?
No, actually what you can do, and that's something that we have also shown in this latest paper in eCoop, is that let's say that you have a printing function that actually depends on evaluation. So what you can do is that you can express this dependency by a constraint. So you can say something, well, this will work as long as my type is constrained in a certain way. It depends on having this evaluation method available. And so you can actually nicely write the evaluation in a modular way. So evaluation doesn't know anything about printing. And then from the printing feature, you have a constraint that tells you that it depends on evaluation, and it also allows you to call the evaluation method, basically. So you can deal with this problem as well.
Okay, very last one. Yeah.
So you mentioned the vision of the software product lines, and you gave the example of Nokia, which is unclear whether it's very successful in terms of the building of the software. So I'm really interested, what would the validation of these ideas be in the context of large software product lines? How would you see whether, because most of the technical work is valid and also...
Right. I mean, there are several other examples. So as I told you, there's actually a web page with several other examples. I do think a validation is necessary. So I'm not sure, but maybe you have two different questions. One is whether software product lines are a good idea in the first place, and the other one is whether the techniques that I'm presenting are, or how would I validate the techniques that I'm presenting. So for the first question, I think, just the fact that so many companies are using software product lines should tell you that, companies really believe in this technology. So actually, I believe that's kind of the justification for, software product lines are a good idea. But for the second question, yes, we do need to, what we need to do is really to study, to see if we can model existing software product lines, existing large software product lines using these techniques. And I think this still requires a little bit of research and effort. So I think what I've shown you is promising, but is perhaps not the complete story yet. So I think we still need to do some work and really try out a large software product line.
Okay, in the interest of time, I think we better wrap it up, but let's thank Bruno for an excellent talk.